I want to talk to you today about the geometric sequences and series and go through a couple of examples that they seem to be quite interesting. So very quickly, a geometric sequence is a sequence that starts with the first term, let's say U1, and every subsequent term is the product of the first term and the corresponding ratio R. So that's going to become the U2, and then if I multiply by R again, I'm going to get the U3, and you get the idea. Now, another way of writing this relationship would be that, of course, the U1 is the first. Then the U2 would become the U1 multiplied by the ratio. Then the U3 would become the U1 multiplied by the ratio squared, and so on and so forth. So therefore, the UN is going to become U1 times by the ratio n minus 1 times. And that is essentially the nth term for the geometric sequence. What does help in many questions, should you come across those, would be that the ratio is equal to the U2 divided by U1, which is also the same as the U3 divided by U2, which is equal to UN divided by the UN plus 1. UN minus 1, actually. So that's another relationship that it's not being given to you, but it does really help when we solve equations. Now, if we go back and look at the sums of the geometric sequence, we have two different formulas. The one that you can find in 1-3, and this is the sum of the finite terms. So otherwise the Sn, that means finite terms. And that happens for when the absolute value of R is bigger than 1. So we're talking about situations where the first term could be anything, but then the ratio has to be bigger than 1. Because if the ratio is between 1 and negative 1, then we are talking about a different scenario. We're talking about the relationship at 1/8, which is the sum to infinity, and that's an important part to understand. And that can only happen for absolute value of R smaller than 1. Essentially, we are looking for the ratio to be anything between 1 and negative 1. So anything in between those two. But of course, the ratio also cannot be 0, because in this case, we wouldn't be having a geometric. Now, the question I've decided to kind of work through is the example 1, or the question 1, which is the 3 times 2/5 to the power of k. And it's been given to you in the sigma notation. So that's sigma that you see here, right? It's read as sigma. That's a Greek letter and stands for the first letter of the word synolo. And then synolo means essentially sum. Hence, you might end up finding questions that they ask you to calculate, let's say, the S15, or they could ask you to calculate the corresponding with sigma notation from n is equal to 1 until 15 of some sort of nth term. Briefly, the benefits of using the sigma notation is that you could, should you wish to, calculate a sum of terms that they don't go from 1 to 15, but let's say they go from n is equal to 5 until 15, and let's just use a 3n plus 2 as my nth term, which is clearly an arithmetic sequence, but that's the one little difference to be able to understand, that the S15 will never start halfway through the numbers that you're adding, whilst the synolo provides you with an opportunity to do from 5th to the 15th. Of course, there's always going to be a way of coming from this one backwards, because if you want to turn that sigma notation from 5 to 15 into an S notation, then it's enough to write that this one is going to be the S15, take away the S5, and that's going to become the sigma notation of n is equal to 5 all the way to 15. Finally, Don't forget the basic thing that the calculator has a special button for that notation where you can type in the variables and you can get your answer straight away. So let's go and see the first question that it seems we have neglected. What we have the sum of terms from 1 until infinity of 3 times 2 over 5 to the power of k. Now, essentially, we want to see what is that generating. Not that you always have to do it, but it would be nice as a first exercise to kind of like generate the first terms. So for k is equal to 1, what do I get? It's going to be 3 times by 2 over 5 to the power of 1. That's going to give us 6 over 5. For k is equal to 2 and k is equal to 3, we'll stop the video and generate it, so we just sort of save a bit of time. Right, as you can see, I just quickly substituted k1, 2, and 3, and I have the corresponding values, which of course they're going to be for the corresponding terms. Now, what I wanted to check is whether this is a truly geometric sequence that I have in front of me. So let me just write down the terms. So the u1 would be 6 over 5, and then the u2 becomes 12 over 25, and then the u3 becomes 24 over 125. So in order to find the ratio, right, and to test what this is going to be a geometric sequence, I can calculate the ratios. So finding the u2 divided by u1, that would become 12 over 25 over 6 over 5. Let's just turning both fractions as fractions over 25. That's going to stay as it is, 12 over 25. This one would become times by 5 to become 25, and times by 5, so that would become 30 over 25. The final answer is going to be 12 over 30, which is the same as 6 over 15, which is the same as 2 over 5. So that's the ratio. I mean, I don't know if you remember the question, but that 2 over 5 seems to be quite expected. If I do the same to calculate the ratio, right, because both cases I'm calculating the ratio. So in order to confirm that this is a geometric sequence, right, I need to find the ratio between 3 consecutive terms. Otherwise, I cannot just make that assumption. Of course, this is just a testing, right? The question is not asking me to do that, but I think it's good for us to understand what's going on. So if I divide the 24 over 125 by 12 over 25, that would become, again, let's make them both fractions over 125. So times by 5, that's going to become 60 over 125. The final answer is going to be 24 over 60. And then 12 goes 2 times into 24 and 5 times into 60. So there you go, the ratio for both, for the terms between the first and the second and the third is equal to 2.5. If we look at the question now, right, which was to find the sigma of k is equal to 1, from 1 to infinity, of 3 times 2 over 5 to the power of k, well, we understand where is this ratio 2 over 5 sort of kind of like appears, because that is your ratio, after having tested this is a geometric sequence. Now, based on the formulas, right, this is the sum to infinity, which is going to become u1 over 1 minus the ratio. The u1, we know that is equal to 6 over 5, over 1 minus the ratio, which is 2 over 5. That will end up being 6 over 5 over 3 over 5, because the 1 is 5/5, and the final result of all of that will become 6 over 3, which is equal to 2. Now, that's one sort of kind of like long solution. there's a better way and a faster way. So let's go and explore that way. So let's switch into a different color. The same question then here, based on properties of series, can be written as the sigma with the 3 outside because it's a common factor from 1 until 8 of the 2/5 to the power of k, which is the same as 3 times, and then this is always going to be, it looks like it has an exponential form, it's always going to be a geometric sequence, with the first term being 2/5. You get it if you substitute k is equal to 1, and the ratio, which is 2/5, because it's like more than obvious now what the ratio is going to be. So that's going to be 3 times the sum of u1 over 1 minus r, which is the infinite sum of that part. Let's put the proper times. That's going to become 3 times the u1, which was 2/5, over 1 minus 2/5, which also is the ratio, because now my first term is 2/5 and my ratio is going to be 2/5. Anything that's going to be in the form a to the power of n, it's going to have a first term, which is a, and a ratio, which also going to be the same a. So that's a very convenient format for us to see things, right? That's going to end up with 3 times, and I have the 2/5 at the top over the 3/5 as the denominator. Let's carry on over here. That's going to become 3 times of 2/3. If you cross out the 3 with the 3, the answer is going to become 2. Way faster, super nice way of kind of like, answering the geometric sequences.